Hey guys, this is Aaron Carmen from AXE Electronic, back with the next video in my series of videos covering basic circuit analysis. So in the previous video, we talked about capacitors and the role they play in our DC circuits and how they behave in a transient sense, so how they behave as time passes. So today what we're going to look at is the next fundamental building block, the inductor. So inductors are going to function very similar to capacitors, but they do have some differences. But like capacitors, they bring a sense of time into our circuits, because before, when we were dealing with just resistors, resistors are time independent. Okay, the voltage across the resistor is going to stay the same regardless of what time you check it. Whereas for an inductor or capacitor, the voltage will change depending on how time passes. Okay, so there's a little analogy that I like to think of that helps me kind of keep things straight with capacitors and inductors. Okay, so the way I think of it is I like to associate capacitors with voltage and inductors with current. Okay, because capacitors, remember, they store energy in their electric field and they like to keep a constant voltage. Inductors like to keep a constant current. Okay, so that's the way that I kind of like to think about capacitors and inductors. So the first thing that we're going to do is I'm going to go ahead and give you the symbol for an inductor. So on the whiteboard here, I will say this is the symbol for an inductor. Okay? So there's actually a couple of different symbols that you can use. One of them looks exactly like a coil, like this. Okay? And another one, and this is the one I prefer to use, just has bumps like this. Okay, I think that second one is a little bit neater, but it's really up to you. Whichever one you want to use. Those are both the same thing. Okay, so an inductor has a quantity called inductance. Inductance. Okay, and its unit is henries, or just a capital H. So you could say that there's an inductor with 1 millihenry of inductance, or a 1 Henry inductor, or anything like that. Okay, so one thing you might notice if you look at this symbol here is that it looks quite a bit like an electromagnet or a coil, and that's because all an inductor is really is just a coil or an electromagnet. Okay, because what it's doing is that whenever current flows through an electromagnet, it's going to be storing energy inside its magnetic field. So it's going to set up a magnetic field, and that's where it's going to be storing its energy. Now remember, capacitors store their energy in an electric field. So inductors, the only difference is they're storing energy in a magnetic field. Okay, and the way you get energy in a magnetic field is through current. So the way you get energy in an electric field is through voltage. That's why we say capacitors kind of store voltage and like keeping their voltage constant. Now inductors, they're storing current. Okay, so you can like to see, or you can think of them as wanting to keep their current constant. Okay, that's why I said before that if you can relate capacitors and voltage, then you can relate inductors and current. Okay, so like we said, like a capacitor, an inductor is going to store energy in a magnetic field. Okay, so let's look at a little simple example up first so we can kind of see how it behaves. So the first example I want to look at is charging an inductor. Okay, so let's say we have this source that I'll call Vs and a switch that is open, and that is connecting a resistor and an inductor. And we'll just call that resistor R and the inductor L. Now, like capacitors, we're going to say this switch closes at time t equals 0. So just to review, if you're looking on a graph at time t equals 0, that's when that switch is closing. So that's when we're going to see most of the action happening in this circuit, whenever that switch is closing. Okay. So the fundamental equation for an inductor that the physicists and mathematicians have identified is that the voltage across an inductor is equal to its inductance times the change in current through the inductor, or change in time. So you can see it's pretty similar to that capacitor, or the fundamental equation for a capacitor that says the current through a capacitor is equal to its capacitance times dV dt. Okay, so it's very similar. Like we said, it's capacitor is C dV dt, inductor is L di dt. Okay, so that's why I like relating capacitors and voltage and inductors and current, because they're very analogous in that way. Okay, so once again, I'm not going to derive the whole differential equation because it's sort of complex, kind of upper level, and I just want to get a fundamental understanding of what's going to happen in these circuits. Okay, so I'm just going to go ahead and skip down, and I'll give you the answer. Now, before I would give you the equation, or in capacitors, I gave you the equation for voltage first. Now, since we're looking at inductors, I'm going to go ahead and give you the equation for current first, because remember, we said capacitors are related to voltage, inductors are going to be related to current. So I'm going to try and keep that together during this lecture. Okay? So what I'm going to say is the current through this inductor is equal to Vs divided by R, okay, open parentheses, 1 minus e to the negative RT over L, close parentheses. Okay? And this is for time t is greater than or equal to 0. So after that switch is closed, this is the current through the inductor. Before, whenever that switch is open, there's no current flowing because it's just an open circuit. So we'll just say it's 0 before that switch closes. Okay? So this is the current through the inductor. Now, all we need to do is know the voltage across the inductor, and the equation for that is going to be V sub L is equal to Vs e to the negative RT over L. Okay? And once again, this is for time t greater than or equal to 0. Before, like we said, that switch is still just open, so there's not going to be any voltage across it. So it'll be 0 if t is less than 0. Okay? So again, like capacitors, we have these equations, and you might be wondering, well, how can I make sense of this? You know, what is really happening in this circuit? Okay? So to save you a little bit of headache trying to work through what is actually happening in these circuits, I just went ahead and made up some graphs similar to the way I did for capacitors. So let me get this graph posted, and then we can take a look at it. Okay, so let me zoom out so we can see everything all at once. Okay, and let me, matter of fact, move this graph over here. So what we can see is that before the switch closes, everything is pretty boring, right? Because it's just an open circuit. So there's 0 voltage and 0 current across that inductor. But once that switch closes, you can see, and I'm going to use the blue color for voltage, you can see that the voltage of that inductor just shoots all the way up. Okay, and it reaches that maximum. Okay, and what's interesting is that during that maximum, okay, the inductor's voltage reaches the supply voltage. So if you put yourself in the shoes of that resistor, you have the supply voltage on one side, and then the inductor gives the supply voltage on the other side. Okay, so no current is flowing through that resistor. Okay, so that makes sense for why the current starts off at 0. Okay, but then as time passes, the voltage across that inductor is going to drop. Whenever that voltage across the inductor drops, now you have a potential difference across that resistor. So the current is going to start flowing. Okay, and then you'll see the voltage continues dropping and the current continues rising. Now the voltage, it just goes to 0. After a long time, the voltage across that inductor goes to 0, and the current, you'll see, reaches its maximum. And that maximum is going to be Vs divided by R. So whenever we first close that switch, we can see some weird stuff happening, but then after a while, that inductor is pretty much just a short circuit, right? Because the voltage across it is 0, which is what a short circuit does, and it's letting all the current pass through that it normally would, so it's not providing any resistance, just like a short circuit. So that's one thing that we can sort of generalize from this. We can say in the steady state, so in SS for steady state, meaning after a long amount of time has passed, an inductor is just a short circuit. And if you think about just a coil or an electromagnet, that makes sense, right? Because it's just a whole bunch of wire wound in a coil. Okay, so yeah, it has some inductance, but at the end of the day, it's really just wire, and we say that wires are pretty much short circuits. Okay, so that kind of gives you a little bit of an intuitive sense of why inductors seem to act like a short circuit after a long period of time. Okay, so now we've seen a charging example. Let's go ahead and move down, and we can look at ourselves a discharging example. Okay, so for inductors, it's a little bit trickier. So I'm going to do a little bit different of an example. I'll draw a line here. We're going to look at a discharging example. So what we'll have is we'll have this Vs here. Okay, then that'll go, forgot something. That'll have a resistance that we'll call Rs. You can think of that as the source resistance. Okay, and then we're going to have an inductor here, and a switch here that is closed. And over here, we're going to have another resistor. It's called R. This one is L. And then that switch is going to flip. So it's going to close at t equals 0, like before. So before we start looking at all the math involved in this, let's just try and get an intuitive sense of it. So before that switch closes, what you have is you have a source, a resistance, and an inductor. So what's going to happen, we saw previously in this charging example, if we have a resistance and an inductor in series, that inductor is going to start charging. Okay? So we're going to assume that this has been closed for a long time. So the current going through this inductor, I, is equal to just Vs divided by Rs. Okay? So after a while, we pretty much just have full current going through that inductor. And now what's going to happen is that at t equals 0, we're going to flip that switch, okay? And then we're going to see what happens as that inductor discharges, because right now it's fully charged up. We're going to see what happens whenever it discharges. Okay? So once again, I'm not going to give you all the differential equations nonsense that you might need for this to derive this equation. So I'm just going to give you the final result. So the current through this inductor, whenever it flips, is going to be Vs divided by Rs, e to the negative RT over L. Okay? And this is going to be for time t greater than or equal to 0. So after that switch is flipped. Before, well, if we think about what's the current through that inductor beforehand we said that it was fully charged, so it had been closed for a long time. So before time t equals 0, it's just going to be Vs divided by Rs. Okay? So before we flip that switch, it's just going to have that constant current going through it that's limited by Vs and Rs. So this is for time t less than 0. Now let's look at the voltage. So the voltage across that inductor is going to be R. Now remember, R is different than Rs. Okay, so we have R times Vs over Rs, e to the negative RT over L. Okay. Now, once again, this is for t greater than or equal to 0. And then before that, we said, after a switch has been closed for a long time and an inductor is fully charged, it looks pretty much like a short circuit. So a short circuit is going to have 0 volts across it. That's for t less than 0. So let's take a look at this equation real quick and see, where did we get that? Intuitively, how does that make sense? Well, remember Kirchhoff's voltage law, Kirchhoff's voltage law states that around a closed loop, the sum of the voltage rises has to equal the sum of the voltage drops. Okay? So the current that inductor is going to push is shown here in the blue color. So that current is going to go through the resistor R. So the voltage across that resistor R is just going to be Ohm's law. V is equal to I times R. So we know I because that's given here. So we know I. All we have to do is multiply that by R, and that will give us the voltage across the inductor. Okay? So that's how we got that VL equation. Okay? And it's pretty simple. It's pretty easy to see why we got that. So once again, I don't want to leave you guys hanging or wondering what this looks like. So I did make up a graph. Let me go ahead and get that copied and put in here. So let's take a look at this graph and see what's going on here. So let's look at this graph. You can see that red, or the orange line, is going to be the current. So you can see that before that switch flips, we pretty much just had a constant current, right? Because we're assuming that inductor is fully charged and the current through it isn't changing. Okay? And then the voltage across the inductor, the voltage across that inductor is going to be 0 because it's acting like a short circuit. Okay? But now, once we flip that switch, remember, it's not going to want to change its current instantly. Okay? The same way a capacitor isn't going to want to change its voltage instantly. So what's going to happen is that it's going to try and keep that current, and in order to keep that current going, what it's going to do is it's going to create a voltage drop. Okay? Now that voltage drop it's going to create a voltage to keep pushing that current through this resistor R. So you can see the voltage just very quickly rises. That voltage just quickly rises and then starts dropping down very quickly. And it's dropping down at about the same time as this current is dropping down. Okay? And you can see that they both go to 0. So after a while, that inductor isn't pushing any more current. It's just whenever we first flip that switch, it's going to push a little bit of current into that resistor until it discharges. Okay? So this is what happens when an inductor is discharging. Okay? So one note that I want to make here is that we said that inductors store energy. I'm sure this isn't 100% technically correct, but this is the way you can think about it. Inductors store energy that's proportional to their current, I. Okay, so if you have a higher current, it's going to be storing more energy. Okay, now capacitors store their energy as voltage. Okay, so if we pull a capacitor out of a circuit, it's going to keep that voltage because you can have a voltage but no current, right? But if we pull this inductor out of a circuit, all right, and it's just, it's open circuited, then it's not going to have anywhere for its current to go. So that's what I'm trying to say. We can't just pull an inductor out of a circuit. I'll use an L for an inductor. We can't pull an L out of a circuit. So for a capacitor, we could pull a capacitor out of a circuit, it's still going to be fully charged. If we pull an inductor out of a circuit, it's not going to stay charged. Okay. So one other thing, the next thing we need to talk about is, what is the time constant? Because remember I said that these are pretty similar to capacitors, and capacitors had a time constant. So what's the time constant for this inductor? Well, remember the standard form for this charging and discharging is e to the negative t over tau. Okay. Now ours was e to the negative rt over L. Okay. So using this information, we can arrive to the conclusion that tau is equal to L over R. So that's our time constant. And remember, we said if you have a higher tau or a higher time constant, that means you have a slower circuit. Now I put slower in parentheses or in quotations because it's not really a beautiful way of describing it, but it's a simple way of describing it, that your circuit is just slower and it's going to take more time to react to things. So similar to capacitors, I also made a graph showing the difference or the effect that time constant has on these circuits. So let me get that pasted in here. So what you can see is that if you have a time constant tau is equal to 1, okay, so you have this blue line, and this is the voltage across an inductor. You can probably go check it against the graphs that we've seen before and see the same thing. You can see that this blue line is going to shoot all the way up, and then it comes down, and it's getting to 0 right at about 4, and at 6 it's very easily at 0. Okay, so that took about 6 seconds for it to get to 0 completely. Now for the second one with the time constant tau is equal to 2, okay, meaning it either has half as much resistance or twice as much inductance, then what's going to happen is that it's going to take longer to sort of reach its steady state. So it's going to take longer, and we said before at 6 seconds we were pretty much done for time constant tau equals 1, but for 6 seconds here we still have a good amount of current. It might take us even closer to 10 seconds before we get completely down to 0. Okay, so this kind of shows you the effect that time constant has on these circuits. So if you have a higher time constant, that's going to equate to a slower or a laggier circuit pretty much. Okay. So before we go, I do have one last example for you guys because I don't want to just leave you guys hanging here with any questions. So I want to make sure that I provide plenty of examples. So let's do this last example. Now this one is just a charging example. Okay, because inductors are a little bit weirder and they're harder to kind of get to behave, so I wanted to make this a simpler problem. Because, at least in my experience, inductors typically got simpler problems compared to capacitors. Okay, so once again we have a resistance and inductance and that source. So this switch closes at t equals 0. This resistance is 2 ohms and this inductance is 1 Henry. All right. So now we can just use the equations that we derived above. We can say the voltage across this inductor is equal to Vs times e to the negative RT over L. And if we substitute in our values, what we'll get is 10 e to the negative 2t. Okay. So this is going to be our voltage across the inductor for time t greater than or equal to 0. Now, ask yourself, what's the voltage across the inductor before that? Okay, so take a second and think about that. Now, what you should come to find out is that, well, it's just an open circuit. There's no current flowing through it. So if there's no current flowing through it, there's no changing current, then the voltage is probably equal to 0. Okay, and you'd be correct. So the voltage is going to be equal to 0 before that switch is flipped. Okay, so now let's look at the current. So the current through this inductor, it's going to be Vs divided by R times 1 minus e to the negative RT over L. Okay, that was the formula that we derived before. So we can see that this is going to be equal to 10 divided by 2, or 10 volts divided by 2 ohms, which is going to be 5 amps. Okay, I wanted to specify amps so that we know that this is current. And then times 1 minus e to the negative 2t. Okay, and this is for t, once again, greater than or equal to 0. Now, if you challenge yourself again, ask yourself what's the current before that. Well, you should get the same reasoning. If it's an open circuit, the current's going to be 0. So t less than 0, you have 0 amps flowing through that inductor. All right, so now we know the voltage and the current. Let me go ahead and plot this for you one more time. That way you can just see the specific answer. Let me get that put for you here. Okay, so this is what we're going to see. We're going to see that initially, like we said, the voltage and the current are both equal to 0 here. Okay, so they're both equal to 0 before we flip that switch. Now, what happens is that whenever we flip that switch, the inductor is going to resist a change in current, so it's going to increase its voltage as high as it can go to resist that current, and then it's going to start decaying. Okay. Similarly, the current is going to stay 0, and then it's going to start increasing. Okay, and then it'll reach its steady state at 5 amps. You can see here, this is 5 amps, and then the voltage reaches its steady state of just 0. So you'll notice if we just didn't have this inductor in this circuit at all, and I'll use the green color to show you the current. If we just didn't have the inductor in this circuit at all, the current would just jump up, and it would look like this. Okay, so if you can see that green color, let me make it a little bit thicker. See, the current would normally just jump up and keep going. But when you add the inductor to the circuit, that's going to make it take a little bit of time to ramp up, okay, before it reaches that steady state value. Okay, so this is about everything that I have for you. One last thing that I wanted to give you before we go is that I wanted to give you a little bit of a thought question, okay, because inductors are a little bit weird, so it can help to think about some things that might happen if you're doing certain things in certain circuits, and this is going to lead you to something that's pretty important to know in a career of electrical engineering. So I'm going to give you a circuit like this. So you have Vs, okay? And then you have a resistor, an inductor, and then down here at the bottom you have a switch that's been closed for a long time. Okay, so this inductor is fully charged. Okay, and then you have R and L, just to make it clear that that's a resistor and inductor. So we're going to say, what happens if you have an inductor in this configuration? What happens if we open the switch? Okay, so what happens if we open the switch? And I'm going to add a little caveat here. After it has been closed for a long time. So after it has been closed for a long time means that that inductor is pretty much fully charged. Okay, let me clear that up. Now you don't have to make out my bad handwriting. So after it has been closed for a long time. So we have this circuit, we close that switch, we let all the current flow through it, and it's charging and charging, and then it's fully charged. Okay, so then after it's fully charged, or after we've left it going for a long time, what's going to happen if we just kick that switch open? Okay, so I'm going to ask you a more specific question that'll kind of lead into it. What happens to the current? Okay, and let me label the current here. What happens to the current? I. Okay, and then I'm also going to ask, what happens to the inductor's voltage? To the inductor's voltage. Okay, now the hint I'm going to give you, because this is a little bit, you have to do a little bit of thinking. I don't want to leave you hanging. So the hint I'm going to give you is this. Remember, the voltage across an inductor is equal to the inductance times di dt. Okay, so just think about this. Think about what you think is going to happen. Try and check your own thoughts, make sure everything is making sense in your own mind, and then in the next video I'll go ahead and give you the answer to that. So that's everything I have for capacitors and inductors. And the next video, what I'm going to do is we're going to get on LT Spice again. I'm going to show you how you can simulate these circuits in LT Spice so you can get a sense of what's going on and maybe double check your own thoughts and make sure you're doing everything correctly. So, like I said, next time we're going to be looking at LT Spice. I think it's going to be a pretty good one, and we can see some interesting stuff happening in these circuits, and you can learn a lot. So if you have any questions, please feel free to leave them in the comments below. If you like this content, please give me a thumbs up and subscribe for more. Otherwise, I'm Aaron Carmen, and thank you for watching.